This video is about solving radical equations, and before I do an example of solving a radical equation, I want to talk about what exactly makes something a radical equation. Well, it's a radical equation if you have a variable under a radical sign, or if you have a variable that is raised to a rational exponent that can't be reduced to an integer. So, I mean, you could write anything. I could write this as 3 over 3, and then that's a rational exponent, but it could be reduced to 1, which is an integer. So this last one, is actually not a radical equation. It has a radical sign in it, but no variable under the radical sign. Okay, so let's solve this radical equation. The first step is to get all of the stuff under the radical sign by itself. So let's add 6 to both sides, and now we have the square root of 5x plus 1 is equal to 6. The next step is to get rid of this radical sign, and the way you do that is you square both sides. The square root of something squared is that thing itself, and it's now equal to 6 squared, so 5x plus 1 is equal to 36, and now we just have a linear equation to solve. We have 5x is equal to 35, which means that x is equal to 7. Okay, let's check our answer and see if x equals to 7 works. 5 times 7 plus 1 minus 6 should equal 0. That's the square root of 35 plus 1 minus 6 equals 0. Square root of 36 minus 6 equals 0, and this is in fact true. So we do have a solution. X equals 7 is a solution. Okay, what about if you have something raised to a fractional exponent? Well, this is the same thing. I could rewrite this as 2 times the cube root of x minus 2 squared is equal to 50. And you can solve this in whichever form you prefer. I actually prefer this form. But if we're going to solve it, the first thing we need to do is get this stuff by itself that has the rational exponent. 2 is not being raised to the 2/3, and we're solving for the variable anyway. So let's get 2 on the other side of the equation. We now have x minus 2 raised to the 2/3 is equal to 25. Alright, so now what do we do? Well, there's a couple ways to solve this problem. The first thing that you could do is you want to get rid of this fractional exponent. One way to do that is to raise everything to the power of the denominator. The denominator is 3. When I raise both sides to 3, when I multiply out this left side, I'm now going to have x minus 2 over 2/3 times 3, and the 3's are going to cancel out, and I'll just be left with x minus 2 squared. On the right side of the equation, I'm going to have 25 to the 3rd power, which is going to be a big number. I'm going to just leave it like that for a second because I'm about to take the square root of both sides to get rid of this 2. Now I'm going to take the square root of both sides, and remember, when you take the square root of something or any even power, you need to put plus or minus. So this is equal to plus or minus the square root of 25 raised to the 3. Let's see if we can simplify this. 25 raised to the 3rd power, the square root of that, that's the same thing as 25 to the 3 over 2. And 25 is the same thing as 5 squared, so I have 5 squared raised to the 3 over 2. 2 times 3 over 2 is just 3, so now it's 5 cubed, which is 125. So I can come down here, and I can say x minus 2 is equal to plus or minus 125, and add 2 to both sides, and I get x is equal to 2 plus or minus 125. Well, 2 plus or minus 125, 2 plus 125 is 127, and 2 minus 125 is negative 123. So I have 2 solutions that work here. You can plug those in and check to see, do both of those solutions work? Okay, now there's a different way that you can solve this problem, but you have to be careful. You have to remember that anytime you have an even exponent up here, then you're going to have to use an absolute value symbol after you solve it. And I'll show you that in this example. So the first step is the same. We're going to divide by 2 again. We have x minus 2 to the 2/3 is equal to 25. Now the other way that you could do this problem is you could raise both sides of this equation to 3 over 2. Doing that, when you multiply these two exponents together, they go away and you get 1. And you have x minus 2 is equal to 25 raised to the 3/2. The problem with this is if you had an even exponent up here, you need to use the absolute value symbol down here when you raise to the 3/2, because that exponent up here is the same thing as saying x minus 2 squared, and whenever you square something or when you raise it to that even exponent, it has that magical quality of turning everything into a positive number, even if it was a negative number. So when you do the inverse of that by doing 3/2, you're kind of losing that quality, and so you need to make sure that you keep that quality by using the absolute values. We saw that 25 raised to the 3/2 is the same thing as 5 squared raised to the 3/2, which is equal to 5 cubed, or 125. So we have the absolute value of x minus 2 is equal to 125. Then if you remember from solving absolute value equations, that means you have two cases here. You have x minus 2 is equal to 125, or x minus 2 is equal to negative 125. If this expression here evaluates to 125, and I plugged that in here, the absolute value of 125 is 125, so that would work. If this expression evaluated to a negative 125, if I plugged negative 125 in here for that expression, I will get the absolute value of negative 125, which is 125. So these two will work. Now I can add 2 to both sides, and I get x is equal to 127 from this first equation here, and then from the second equation I would get x is equal to 2 minus 125 is negative 123. So you get the same answer either way. If the exponent is odd, let's say this was 2 times x minus 2 to the 3/2 equals 50, then you don't have to worry about that absolute value, because that 3 doesn't kind of have that quality of turning negative things into positive. But anytime that's an even number in the numerator, you have to worry about it. So if this was x to the 6/5 equals 12, then I could solve this by raising it to the 5/6 on both sides. But when these cancel out, I need to remember to write the absolute value of x is equal to 12 to the 5/6, so that I get both of those solutions. All right, let's solve this equation. So we're going to get the radical by itself, subtract 5 on both sides. You get the square root of x minus 3 is equal to x minus 5. Now we're going to square both sides to get rid of the radical sign. Square, square. X minus 3, the square root of x minus 3 squared is just x minus 3. And the right side of the equation is going to become x squared minus 10x plus 25 when you expand this binomial. A common error I see here is students will say, well, that's x squared plus 25 or x squared minus 25, because you just square this term and square this term. It doesn't work that way. X minus 5 squared is the same thing as x minus 5 times x minus 5, which is equal to this expression down here. Okay, so now let's put all of this together on the same side of the equation. So I'm going to subtract x and add 3 to both sides, and I get 0 is equal to x squared minus 11x plus 28, and I'm going to factor this, and I get x minus 7 times x minus 4. 7 times 4 gives me 28, and negative 7 plus negative 4 gives me negative 11. So x equals 7 and x equals 4 are the two solutions to this equation. Let's check them. X equals 7 and x equals 4. Let's plug them back in. Okay, so plugging in 7 first, I get 7 minus 3 plus 5 is equal to 7. Square root of 7 minus 3 is the same thing as square root of 4, which is 2 plus 5, which is equal to 7, which works. So our first one we got right. Now let's check x equals 4. Square root of 4 minus 3 plus 5 is equal to 4. Square root of 4 minus 3 is 1, plus 5 equals 4. Square root of 1 is 1. 1 plus 5 equals 4. This does not work. So x equals 7 is a solution, and x equals 4 is not a solution. Why did that happen? Well, when you have a variable that's inside a radicand and a variable that's outside of a radicand, you often get an extraneous solution. Maybe you always get an extraneous solution. I'll let you check and see if you can find one where you wouldn't get an extraneous solution. Okay, when you have decimals as an exponent, these can be written as fractions. So I could write this as 2x plus 1 to the 1/2 minus 3x plus 4 to the 1/4 equals 0. It's whatever you prefer. I'm going to just leave it as decimals for now. So what I want to do is I want to solve this. I want to get a radicand by itself. So I get 2x plus 1 to the 0.5 is equal to, I'm moving this entire term to the other side of the equation. So I moved this entire term to the other side by adding it to both sides. Now I say these two expressions are equal. All right, so what's the next step? You want to raise both sides to something that will make the fractions go away. Well, if I raise both sides to 2, I'm still going to have a fraction over here. 0.25 times 2 is 0.5, so that doesn't help me. If I raise both sides to 4, however, 0.25 times 4 is 1, so no fraction over here, and 0.5 times 4 is 2, so no fraction over there. So this is 1/2, and this is 1/4, so I'm going to raise both of them to the least common denominator of these two rational exponents, which in this case is 4. So 2x plus 1, let's do the left side. 0.5 times 4 is 2, so now I have 2x plus 1 squared. And over here, I have 3x plus 4, because 0.25 times 4 is 1. And we just had 1 in the numerator, so we don't have to worry about that absolute value problem. Okay, so now let's square this left side of the equation, and that will give you 4x squared plus 4x plus 1 is equal to 3x plus 4. Let's move everything to the same side of the equation. And we get 4x squared plus x minus 3 is equal to 0. Let's see if we can factor this. To test if we can factor it, let's look at the discriminant. The discriminant is b squared minus 4ac, which in this case is 1 minus 4 times negative 3, which is 1 plus 48, which is equal to 49. The discriminant is a perfect square, so we actually can factor this. We know that we're going to get the square root of 49 as a perfect square. You could go ahead and use the whole quadratic formula on that, but let's go ahead and factor. Let's do 4x and x, and let's see, this middle term is positive, so I'm going to say plus 1 minus 3. This is what that will factor to. Those two things are equal, which means x is equal to 3/4 or negative 1. All right, so you should check these two to see if one of them is an extraneous solution. So we're going to check x equals 3/4 and x equals negative 1, and I'm going to kind of cheat for the sake of time. I already know negative 1 doesn't work, so I'm going to plug that into you and show that. 3 times negative 1 plus 4 to the 0.25 equals 0. All right, 2 times negative 1 is negative 2 plus 1 raised to the 0.5 minus negative 3 plus 4 raised to the 0.25 equals 0. This is going to be negative 1 to the 1/2. Uh-oh, that's not a real number. This is the same thing as the square root of negative 1, which we know is I. So here's a problem. We got a negative number here. The second term doesn't cause a problem. We've got 1 to the 0.25. This is just 1, but we have I minus 1 equals 0, and that's not a real solution. So this is the only real solution. It's the value that you can plug in for the variable that will make this statement true. So always check your two solutions if you get two solutions for extraneous solutions. And that is it for this video.